Good evening. So today we'll start the second class in this series of stochastic processes. So last class we covered just the basic introduction, the motivation, and what all will be covered in this course. So second class, last class we also saw definitions of probability space. What are the what are the three main things that goes into the probability triplet to form the probability space, and we saw some properties of the probability measure. So we'll see one more probability of property measure, which is the um, continuity of probability. But before that, since we saw that probability measure is on events, and we saw that events are subsets of the sample space, so we need to familiarize ourselves with some properties of sets. So first we'll talk about what is the limit of a set. Uh, so the question. We have basically two types of sets. So when I write this, I mean these are a sequence of sets, not a set of sets, but a sequence of sets. So you have an ordered, so A1 is a set, A2 is a set, and they have a particular order to them. So A1, A2, A3, A4. So this is known as a sequence of sets. So if these sets are non-decreasing sets, so what do we mean when I say that these sets are non-decreasing is, um, so you have A1, the first set, then the A2. A1 is a subset of A2, then A3. They're not decreasing. They're not decreasing, they're increasing, and so on. So these types of sets are known as non-decreasing sets. So for these type of sets, we have limit n tends to infinity, an is equal to the union of all the sets in the sequence. Similarly, if we have an a sequence of sets which are non-increasing. So one, okay, so let me write here. What does non-decreasing mean? That an plus one is a subset, is a superset of this comprises a non-decreasing set. Yeah. So what do we mean when I say they're non-increasing sets is, so you have A1 and you have a decreasing subset A2 and then go to A3 and this comprising set. So what do you mean is an plus 1 is a subset or equal to n. Then these are non-increasing sets or decreasing sets. So the limit of non-decreasing sets is intersection of all the sets in the sequence. Okay, so now uh, these are for sequences which are non-decreasing and non-increasing. So what happens if you don't have a particular order of these sets? If you just have some sequence of sets, then how do you come up with sets? So for any general sequence n such that n belongs to n. So these are a sequence of events, not specified whether they are increasing, non-decreasing, or so here let me highlight these. So these are non-decreasing, these are non-decreasing. When they're not specified, they are non-decreasing or non-increasing. They are just a sequence of sets. So for this, we have some very good definitions of lim sup and lim inf. So lim sup n tends to infinity of the sequence of sets is equal to intersection, union, and lim inf. These are the two definitions. So now for any general sequence. This is for any sequence of sets. There did not be any non-decreasing or non-increasing. The limit of these sequences exists if and only if lim sup the sequence equal to limit of the sequence. Under this condition, we say that limit exists. Okay. So before that, we'll prove a small lemma. The intuition behind lim sup and lim inf we'll see shortly when we look into more random process, or where we look at events uh, with random process with stochastic processes. Because stochastic process will have events such as this, which are increasing or decreasing, or some sort of so we'll see more later, the intuition behind this later. But I'm just setting up the math here. So um, one lemma is given a sequence of events an, lim inf of an is a subset of lim sup of an. So this is always true, irrespective of if the limit of the sequence exists or not. This is always true. So all we need to show that a limit of a sequence exists is to show that mm, lim inf is a superset of lim sup. If we show this is already true. From 1 and 2, we get that the lim inf equal to lim sup and the lim exists. So yeah, to make our work easier, we'll show for any general sets, the lim inf is always a subset of lim sup. So yeah, how do we move on into that? So let's write the proof. So we have um, so now let's define En as union of m greater than n An. Okay, so what we are doing here is so let me write this down more clearly. So what we're doing is, so E1 will be A1 union A2 union A3 and so on. E2 would be A2 union A3 A2 union A3 union A4 so on. E3 would be A3 union A4 union so on. So basically what you're doing is you're taking away stuff from each of the as you go deeper into the sequence of E's, not the A's. So uh, what you have here is En plus 1 would be a subset of En. Now, what we see here, if En plus 1 is a subset of En, then we have seen that it is a non-increasing set, so it is a decreasing set. So this is a non-increasing sequence of sets. Ens are. So this is the observation that we made. So we have defined something using the sets and we have created non-increasing sequence of sets. Similarly, we can write Fn intersection n greater than an. Okay, so what are these? So F1 equal to A1 intersection A2 intersection A3. F2 is A2 intersection A3. F3 is A3 intersection 1. Okay, so in the intersection, as you remove away sets from it, what you're doing is you're placing more constraints. As you add more sets to it, you're placing more constraints and you're removing stuff from it. So um, here, what does my claim is? If X belongs to F2, then it implies that X belongs to F1. Sorry, the reverse. If X belongs to F1, then implies that X belongs to F2 because F2 and F1 have this part common. So if X is an element in F1, then X will belong to F2. But suppose if X belongs to F2, that does not imply that X will belongs to F1 because there is a case where X need not belong in A1. If X is not in A1, then X is not in F1. So what does this give? So it gives that all the elements that are in F1 are in F2, but all the elements that are in F2 are not in F1. So what you basically get is F1 and then F2. All the elements in F1 are in F2, but all the elements in F2 are not in F1. So F1 is a subset of F2. So you get F1 is a subset of F2. Similarly, this can be done using induction to show that Fn plus 1 of Fn is a subset of Fn plus 1. I hope this is clear. So from this we can claim that Fn's are non-decreasing sequence of sets. Okay, so what have we done till now? We have made two sequence of sets, one which are non-increasing and one which are non-decreasing. Okay, so some more observations from these two. So we have F1, F2, so on till Fn. These are all subset of An. Okay, so how do we see this? So An intersection continue, An intersection continue, An intersection continue. This if I extend to Fn, this will have um, just a second. So this if I extend till Fn, this will have An intersection. But then Fn plus 1 will not have An. It will start from An plus 1. So as you can see, all these F1 to Fns contain some element of An. So if X is in F1, F2, F3, F4, Fn, then it is in An. But the vice versa is not true because you can have an X which does not belongs to A3 and so it will not belong to F3. I hope this is clear. So this is first observation. F1 to Fn are subsets of An. The second observation is Fn is a subset of An for all in greater than or equal to n. I hope this is also clear because Fn for any n would contain An. It will also contain An plus 1. It will also contain An plus 2. It will also contain An plus 3 and so on. Okay. So these two observations are clear. So now next what we do is um, we take F1. Hmm. So what we do is we take the unions of all these sets. So basically what you have is you have uh, sorry, F1 is a subset of AN, F2 is a subset of AN, so on till Fn is a subset of AN. And Fn plus 1 is a subset of AN plus 1, Fn plus 2 is a subset of AN plus 2. So these constraints come from the first observation, the first n, and the next from the second observation. So now taking unions of all these sets, what we get is union I belongs to the natural numbers. Fi is a subset of union m greater than or equal to n a n. As you can see, on this side you have all the f's has the index of all the natural numbers, but on the right side the index of the a set sequence starts from n. So this is for all n belongs to m natural numbers. Then so so what you can write is, so this will again form a sequence of equations. So what you can write is union I belongs to n F5, the subset of union m greater than or equal to 1 A1. Union I belongs to n F5, the subset of union m greater than or equal to 2 AN, AN, and so on. Now, since these are a subset of each other, the intersections of all these also should be a subset of this. So what you get is union I belongs to n F5 is a subset of intersection n belongs to n union m greater than or equal to n AN. And what is Fi? When we have noted from here, Fi's are intersection m greater than or equal to AN. So we have union I belongs to n intersection AM m greater than I is a subset of intersection n belongs to n union m greater than or equal to n AM. From the definitions we have, this is the liminf of AN in tensor function, which is subset of lim sup AM, AM and tensor. So what have we done till now? We have shown that given any arbitrary set of sequences, the lim inf of those sets is always a subset of the lim sup. So to show that limit exists of arbitrary sequence of sets, we just need to show that the lim sup is a subset of lim inf, and we are done. Okay, so we also saw the definitions of what lim sup and lim inf of any general sequence of set means. So next we'll see continuity of probability. Okay, so continuity of probability, we'll first do it in three divisions. So the first part is we'll show it for continuity of probability for increasing sets, increasing sequence of sets, then continuity of probability for decreasing sequence of sets. Then we'll show it for general sequence of sets. Because showing for general sequence of sets, we need to use the continuity of probability for increasing and decreasing sets. So first part. Um, AN is a sequence of sets, which is okay. First, let me write what I want to show for continuity of sets. So limit n tends to infinity, probability of AN equal to probability of limit n tends to infinity. So this is if so AN, this is a sequence of sets which is given if the limit exists, that is limit n tends to infinity AN is A, then this is probability of A. This is the definition of continuity of probability. So now we'll try to show this. For this is the property of probability measure. So this will try to show this when the sequence of sets are increasing. So we know that the sequence of sets are increasing. Now what we want to try to do is we want to try to make disjoint events and use the property of union bound to not union disjoint events add up the property that uh, disjoint events the countable additivity of probability measure to show this. So that is what we are trying to do. So what we have in there increasing, we have so A1, A2, so on. Okay. Hmm. So first let's create a sequence of disjoint events, FIs. How do we create FI? So first let F1 be F1. This is F1. Then let's create F2. This ring is F2. So F2 is A1 intersection A2 complete. And so on. You can write Fn as An intersection union of I equal to 1 to n minus 1 Ai whole constant, which is basically equal to An intersection An minus 1 complete. Because you know that As are increasing. From this, we can show that the union of I equal to 1 to infinity Fi equal to union of I equal to 1 to infinity Ai, and union of I equal to 1 to n Fi is also equal to union of I equal to 1 to n Ai. This is A2 intersection A1 component. So now, what we're trying to show? We're trying to show the probability of limit n tends to infinity an. This is equal to probability of limit of probabilities. So now, since we know that ans are increasing, and the limit of increasing sequence of sets is the union, we can write this as union. But now we want to use the disjoint sets that we have just created. So this is equal to probability of union I equal to 1 to infinity fi. Since these are disjoint, we can use the countable additivity property of probability measures and write this as sum of probabilities. This we can write as limit of finite sum n tends to infinity sum of I equal to 1 to n probability of fi. Now again, putting it back in terms of probability of union of I equal to 1 to n fi countability, again using countability property but the reverse side, and then we get limit n tends to infinity probability sum union I equal to 1 to n. Here I'm making a mistake, sorry. So the union of all these disjointed disks is just A, because as you can see, union of F1 and F2, you just get A2. It is A1 union A2, you can write it as A1 union A2, but A1 union A2 is A2 because of the property of the increasing property of the sequence of sets. So which is equal to union I equal to 1 to n AI. Similarly, where each you can write as an intersection an minus 1 complement. So this is an. Yeah, you're done. We have showed the relative property for increasing sets. Now let's take the case where they are decreasing. So you have a sequence of events, and this sequence of events are decreasing. So if these are decreasing, then we can say that the sequence of events in complement such that n belongs to n are increasing. So what this means is basically, okay, yeah. So now you have the property, you use the above property of the probability of continuity on increasing sets, and you derive it for decreasing sets. So since they are probability of union I belongs to n complement equal to limit n tends to infinity probability of n complement. So this I can write as 1 minus probability of intersection n belongs to n belongs to n equal to limit n tends to infinity 1 minus probability of n. So probability of limit n tends to infinity an equal to probability of intersection of n belongs to n, an, which is equal to limit n tends to infinity, probability of n. This also. Now using these two, we'll show the third part for any generalized set. So now you have a set of sequences of set an. These are any general, they don't have any structure of increasing, non-increasing, or decreasing, or non-decreasing. We need to show the continuity property of probability on these events of sets. But the main condition you need is that the limit must exist. The limit must exist for these sequence of sets. So for the limit to exist for these sequence of sets, we know that the limit could be equal to the lim sup. If this condition is satisfied, then only the limit is exists. So if the limit exists, so we know that this condition satisfies. And then using this condition, we'll show that the probability continuity of probability also satisfies. Okay, so now let us create two different. So we'll create En union m greater than or equal to n an. So these are non-increasing sequence of sets. I think we use the same. Yeah, so these, and we also seen that these are non-increasing sequence of sets. So it's the same construction again. So we are trying to create a general sequence of sets as non-increasing and non-decreasing. And we have the continuity of probability for non-increasing sets and for non-decreasing sets. And we also know for the general sequence of sets, the limit exists. Using these three, we'll try to show that the probability measure is continuous on these types of sets also. Okay, so from this, we have that an is a subset of en for all m greater than or equal to n. The other side of the thing, we create fn, which is intersection of m greater than or equal to n, an. These are non-decreasing. And from here, we can see that fn is a subset of an for all m greater than or equal to n. So this we have already seen here as observation 2. So this observation 2 is what is this is same as this. This is observation. Okay, so yeah. I'll just write one more extra step here so that you all can understand. This is for all m greater than or equal to n. So now m is varying. So you have mn plus 1 is a subset of en. Mn plus 2 is a subset of en. And this goes on. So now we also have proved the monotonicity of probability in the last class. So using the monotonicity property of the probability of last class, we can say that probability of n is less than or equal to probability of n. Similarly, probability of am plus 1 less than or equal to probability of en. And so on. So since all these are less, the supremum of m greater than or equal to n probability of An is less than or equal to probability of En. Let's keep this on one side. Similarly, on the other side, we have the same thing. Fn is a subset of An. Fn plus 1 is, sorry, Fn is a subset of An plus 1. Fn is a subset of An plus 2, and so on. And in the same way, so from here to here, we have applied probability on both sides and monotonicity, property of probability. So say you apply probability on both sides and using the monotonicity, property of probability, we get probability of Fn less than or equal to probability of An. Probability of Fn less than or equal to probability of An plus 1. Probability of Fn less than or equal to probability of An plus 2. So this is important. We'll use this later. Similarly, here you have, since all these different probabilities are less than some particular term, the minimum of those probabilities also should be less than the particular term. So we can write this as probability of Fn is less than infimum of m greater than or equal to n probability of An. So this is also an important one. We will write it later. Okay, so now we'll have to use the uh, properties that we have derived for continuity of probability for increasing and decreasing sequence of sets. We have two increasing and increasing sequence of sets here. Uh, yes, so next, we know that limit n tends to infinity En exists, and the probability of limit, sorry, probability of limit n tends to infinity En equal to limit n tends to infinity, or the other way around. So limit n tends to infinity, probability of En is equal to probability of limit n tends to infinity En. Which is equal to probability of, since Ens are non-increasing, Ens are decreasing. So we know that this is equal to intersection n tends to n belongs to n En. But we also know that Ens are, what did we formula? Ens are unions of n. So intersection n belongs to m, union m greater than or equal to n am. Now here you, yeah, sorry. We apply limit on both sides. And we get limit supremum of probabilities of n is less than or equal to limit n tends to infinity probability of en. Similarly, you apply limit on both sides, and you get lim sup probability of fn is, sorry, probability of fn limit n tends to infinity probability of fn is less than or equal to limit probability of an. So this is probability of lim sup n tends to infinity an, but we also know that this is um, greater than or equal to lim, lim sup n tends to infinity probability of an. So this is the first equation that we got. Similarly, we can write the second equation where we have limit n tends to infinity probability of fn equal to probability of limit n tends to infinity fn from continuity. But we know that these are non-decreasing sets. And so you have fn, but fn we have created it using intersection and greater than n greater than or equal to n am. This we know as probability of limit n tends to infinity n, but this is less than or equal to limit n tends to infinity probability of n. So we can write this as, finally using these two, we can write this as uh, lim sup of probability of n tends to infinity is less than or equal to probability of lim sup n, which is equal to probability of lim inf an. This part is because limit exists. Whose limit exists? The sequence of sets an. These guys limits exist. That's why this is equal to. But that is also equal to probability that it is equal to the limit of the events, right? And then this is less than or equal to lim inf. So let me write this here. But now from 2. So this part is from 1. This is because the limit exists. Let me use a different color. This is from 1. This is because the limit exists. Whose limits? The sequence of sets limit exists. And then we have this is less than or equal to lim inf probability of A tends to infinity. This again is from 2. So from this we can see that, from 3 we can see that lim sup probability of n tends to infinity is less than or equal to lim inf n tends to infinity probability of A. But we know that lim inf probability of A is less than or equal to lim sup probability of A. So for this both to happen, lim inf probability of A equal to lim sup probability of A, which is equal to the limit n tends to infinity probability A. From the third equation again, you can see that limit n tends to infinity probability of A equal to probability of limit n tends to infinity A. That's right. So this is the total proof for continuity probability. So let me recap again before we go into the next lecture. So what did we see in this is we saw um, what are some limits of sets. If you're given a sequence of sets, what do the limit indicate? So first we have seen for non-decreasing sets and non-increasing sets. Then for any general sets, we define lim sup and lim inf of general sequence of sets. And then using those, we try to come up with some lemmas to show the dependencies of lim inf and lim sup, and what does it mean when you say that a given sequence of sets have uh, their limit to have a limit. We have shown that the lim inf of a sequence of sets is always a subset of lim sup of a sequence of sets. We also made some observations on how to, given a general sequence of sets, how you can create some non-increasing sequence of sets and non-decreasing sequence of sets. Then after that, we showed continuity of probability, where the probability measure is continuous over limits over sequence of sets. You showed this for increasing sequence of sets and then the decreasing, and then using those two, you have shown it for general sequence of sets. So this was one of the property of probability measure, which is very important, which we'll be using to uh, tell more about Borel-Cantelli lemmas. But before that, let me quickly introduce mm, random variables. Okay, so we'll now go into Borel-Cantelli lemmas. So you have a probability triplet or a probability space given by the sample space, the event space, and the probability measure. The first Borel-Cantelli lemma states that you have a sequence of events such that the sum of probabilities of all the sequence of events is less than infinity. Then almost surely finitely many ANs occur. So here this word almost surely means the probability that finitely many ANs occur is 1. If this happens, then we say that the event is almost sure event. Okay. The second Borel-Cantelli lemma states that given a sequence and also the condition that they are independent events such that summation I equal to 1 to infinity probability AI is infinite, then almost surely infinitely many ANs occur. So again here almost surely, again here almost surely means probability of infinitely many ANs occur is 1. So before going into, we'll introduce some mathematical notations for finitely many. Infinitely many. Okay, so the event that infinitely many AIs occur is given by intersection union set. So okay, so unions were defined by ENs, right? Yeah. So let me call this, let me define EN as union M greater than AM. So what does this mean? This means that this is the event that at least one of an plus 1 till infinity has occurred. So the nth tail event has occurred. Similarly, en plus 2 is uh, en plus 1 is union m greater than or equal to n plus 1 an. Even that at least one en plus 1 have occurred. We have also seen that ens are non-increasing or decreasing sequence. So en plus 1 is a subset of en, non-increasing sequence of sets. So now for the first one, probability of an infinitely of n. This is what we're trying to do. So this is probability of intersection n equal to 1 to infinity union m greater than or equal to an, which is probability of intersection of ens. But since ens are not decreasing, this can be written as limit non-increasing, so they're decreasing en from continuity of probability. This is equal to limit n tends to infinity, probability union m greater than equal to n, n. This is less than or equal to limit n tends to infinity. Summation probability an m equal to n to infinity. This inequality is using the union bound because we don't know, because the AMs could be any general state, they don't have any disjoint or any probability like that. So now for the we are given that the infinite sum is less than infinity, and here we have the tail sum. So this is the tail sum of the sequence summation I equal to 1 to infinity probability of AI. Since this tail sum is finite, this the limit of the tail sum would go to 0. Therefore, we have probability of AI occurring infinitely often as 0, which implies probability of AI finitely many is 1. So the first one is the first step. For proving Borel-Cantelli Lemma second proof, we'll prove a small lemma. Suppose you have PIs. So these are basically properties which are 0 between 0 and 1, such that summation of those PIs are not bounded. Then the product of 1 minus PIs will go to 0. So the proof for this is simple. So we know that log 1 minus x is less than or equal to minus x for all x belongs to 0, 1. So log product of p's 1 minus pi's, because pi's belongs between 0 and 1, is equal to log limit of the product of these is less than or equal to log this is due to the fact that um, log is a monotonically in non-decreasing function. Which is equal to summation log 1 minus pi I equal to 1 to k for all k greater than equal to 1. which is again less than or equal to summation I equal to 1 to k minus pi for all k greater than or equal to 1, which implies log I equal to 1 to infinity 1 minus pi is less than or equal to minus infinity. So pi I equal to 1 to infinity 1 minus pi equal to 0. So now we'll do the proof for the second theorem for Borel-Cantelli Lemma. So we have 1 minus probability of n occurring infinitely often is equal to probability of n occurring infinitely complement of n occurring infinitely often. Infinitely often we have defined it as intersection of events, intersection of n greater than or equal to n, which is probability of unions using the De Morgan's law. This is intersection, sorry, n en en complement, which is less than or equal to summation n equal to 1 to 50 probability of en complement. But probability of en complements are summation n equal to 1 to infinity probability of union of n n greater than or equal to an complement probability of, okay, let's do one thing. We'll calculate separately the probability of n complement. So probability of n complement is equal to probability of union I equal to n to infinity ai complement, which is equal to probability of intersection I equal to 1 to n ai complement. This is using the Morgan's law, which is equal to limit m tends to infinity probability of intersection I equal to n to m ai complement which is equal to limit m tends to infinity. Now we'll use the assumption in the second part of Borel-Cantelli's lemma, where we have that um, these are independent events. So since they are independent events, we can rectify the intersections of those events. So since AIs are independent, AI complements are also independent. So this can be written as product of n to m property of AI complement, which is here we have used independence of AIs tends to infinity I equal to n doing 1 minus e of a, which is limit, which is just basically I equal to n to m into infinity 1 minus p of a. This is equal to 0. This is from the fact that this is from the lemma that we have proved above. And if we put this back here, we have 1 minus probability of an occurring infinity often is less than or equal to 0. 1 minus probability of an occurring infinitely often is less than or equal to 0, which implies probability of an infinitely occurring is greater than or equal to 1. Probability measure can't be 1. Therefore, probability of an infinitely of occurring infinitely often is equal to 1. So these are the two Borel-Cantelli lemmas, which says given a sequence of sets and some condition based on the probability measure, you can say which event is almost sure to occur. So if the sum of their events is less than some of the probabilities of the individual events are less than infinity, then only finitely many events would occur. But if they are independent and the sum is infinite, then infinitely many events occur. So we'll be giving two examples for this, like where these have examples. So it will be simple infinite coin toss example. So in the the sample space is given by 0 or 1. So the 0 or 1 means that if you get a head, then it's 0. If you get a tail, it's 1. So first you have AI is an event that ith toss is head, and the probability of you getting nth toss is head is 1 by n square for all n greater than or equal to 1. So from this we can see that the summation n equal to 1 to infinity probability of an is less than infinity, which implies finitely many heads will occur. So this is the inference that can be made using the Borel-Cantelli Lemma. So if you have a sequence of events that you want to do, and you know the probability measure as a function of the time that which that experiment has been done. And as you can see, as the rate at which the probability of you finding a head in the end goes to 0 as you go to infinity. So basically, after some point, you'll not find any hits. The probability of finding a head would be so low that it'll almost be 0. This is intuitive enough. But the first Borel-Cantelli lemma. So now instead of 1 by n, if we take it to be 1 by n for n greater than or equal to 1, we see that summation of n equal to 1 to infinity, probability of n equal to infinity, which implies infinitely many hits will occur. So this is the bizarre part. So the first part is very clear. So you can see that as you keep on tossing the head, the probability of you getting in head is decreasing. The rate at which it is decreasing is very high. Hence, after some point, you will never get ahead. But if the probability of n equal to 1 by n, then Using Borel-Cantelli Lemma, you can say that infinitely many hits will occur, even though it's not intuitive. You can say that uh, infinitely many hits will occur. Okay, so before we end today's class, I'll just give a quick understanding of what a random variable is. I'll just give the definition of a random variable, and then uh, yeah, I think we'll be done for today. Next class, we'll take up some properties of some like concentration inequalities, expectations, conditional expectations for those random variables, and also we'll see convergence of random variables, similar to the continuity and Borel-Cantelli lemma of events. We'll see continuity. We'll see convergence of random variables. But today I'll give the brief definition of random variable. So these three classes would end the introduction part, the basic math part that you need so that you can go into stochastic process. From the next class, we'll um, go into Poisson process. Okay, so random variable. A random variable on a measurable space is a f measurable function x maps from the sample space to the real. So now what is an f measurable function is if you take the inverse map, which is defined as all the sample space as that x omega belongs to the set B, then this should belong to the event space that you have created. This is for all B belongs to the Borel of the real lines. We'll not go into the details of what a Borel set is, but basically what you have is Borel set is basically a sigma algebra on the real lines. So what you have is suppose you have a set which is the sample space and you have the real line. So this is uh, this point is an event. So now this point maps to one point, x of this point maps to one point, but this whole event space is mapped to a set in R using this x. This is x. This point is x of omega. And now you have a same probability space on real line, but this probability of x of any event is just the probability and x inverse of p, the composition of the random variable to the output space, and then normal probability of that. So for that condition, we need this to belong to the event space because probabilities take events which are of event space and map them to a 0, 1. So this is the definition of a random variable. So basically, the definition of a random variable is it maps the sample space to the real line. Okay, so yeah, I'll stop here for today. Next class we'll see some how do you characterize a random variable, what is the CDF for random variable and all, and we'll see also expectations and conditional expectations and convergence of random variables. Thank you. I'll be stopping today's class.